in America. So they were able to do that because they were closely connected to England at that time, and statistics was already a thing in England. So they were trying to adopt the British model. So many of you may have heard of Professor C.R. Rao, who was a famous Telugu statistician. He served about 40 years at the ISI, and also P.C. Mahalanobis is also an eminent Indian statistician. He was actually the founder of ISI. Okay, so from ISI, um, I went to Yale University in Connecticut, where I did my PhD. And then after that, I joined UC Berkeley, and that's where I am right now. So if you go to my website, there are more details about the courses I teach and the kind of research I do, etc. Okay. All right. So for today, I just wanted to maybe give you some overview of what the field of statistics is. It's hard to do a complete overview in one standalone lecture. So I'll be of course selective. I'll try to emphasize topics that I feel are more important and interesting and relevant, and then say something about how the field of statistics relates to some other modern popular fields such as data science, machine learning, and artificial intelligence. Okay. All right. So let's start with if you go to Wikipedia and see what statistics is, so you'll get a definition like this. Statistics is the discipline that concerns the collection, organization, analysis, interpretation, presentation of data. Okay, so the word data is crucial, and yeah. So what this definition does not state is it doesn't say why you need to analyze data. So what is the reason for collecting, organizing, interpreting, and presenting data? So another definition that maybe more statisticians are comfortable with is the following. So statistics is the discipline which formulates principles and develops methods for learning about the world from data. So the goal in statistics is to learn about the world, and the data is supposed to help you to do that. Okay, so now one question that many people ask is why study statistics? Okay, so I'll try to give you three reasons for why statistics should be considered as a field of study by like if you're going to college, for example, why you should take stats courses. So the first reason is some statistical literacy or data literacy is really essential for everybody. Okay, especially in the current world. So for example, so this is a news article from a couple of days ago. This is talking about an election poll. So it says that 39% of registered voters in this particular poll said they would vote for Biden if the election were held today. So this was a couple of days ago, and 38% for Trump. And then there is this interesting sentence which says that Biden's lead was within the survey's 1.8 percentage point margin of error. So that's a technical sentence. In order to fully understand what that means, you need some background in statistics. Okay, so roughly it just says that this 1% lead should not be taken too seriously. Okay, but for a precise understanding, maybe a first course in statistics would be necessary. Okay, so you see things like this in news articles all the time. If you properly want to understand things, some background in statistics is needed. Here is one other very common thing that okay, sorry about the noise. Another common thing that people say is so you go to a doctor with a baby, and the doctor says that the birth weight percentile or the weight of the baby at the current moment is at the 11th percentile. So what does this actually mean? How is it measured? What are the implications of that? Like, should you be worried about the baby and things like that? So again, so some technical terms from statistics come in daily life. So that is so some data literacy. is definitely necessary. Okay, and also in newspapers, you see some sometimes slightly strange headlines. So, for example, this one is from an actual, some kind of a magazine or newspaper. It says, "Why going to university increases risk of getting a brain tumor." So the context for this is from Sweden, where they, in the Scandinavian countries, it's easier to get records of people right from when they are young to actually their hospital records and things like that when they get old. So some group of scientists did a study where they saw that people who went to university, the proportion of people getting brain tumors are actually higher. So then this came out, and then the journal for maybe clickbait came up with a headline like this. Okay, so this obviously sounds nonsensical, and so even if the data is showing something like that, you shouldn't trust it too much. You can come up with some alternative explanations. It could be that people who go to university and are more educated are actually getting checked regularly for brain tumor, and they're registering. If they do get brain tumor, they're actually getting it registered. So therefore you see more of those cases from educated people than from other people. So that could be an alternative explanation. So if you take a Stats 101 class, there is you'll be taught a lot about how to interpret data quality, how to interpret results, and things like that. Okay, so one more slightly strange headline is this, which says that left-handedness is a marker for decreased survival fitness. So what they looked at is they looked at people by age group, and then in each age group they saw how many people were left-handed, and they found that in the older in the older people there are fewer left-handers compared to younger people. So I think they use that to make the inference that maybe if somebody's left-handed, then they're likely to die early. But of course, there are alternative explanations. It could be that in the older generation, people were discouraged to be left-handers, so there are fewer percentage of left-handers among older people. So things like this. So this you might come across headlines like this in news articles and so on. So if you have taken a stat course or something, it's much easier for you to actually figure out what is genuine and what's maybe somewhat fake. Okay. All right, so that's my first reason for why one should study statistics. The second reason is that statistics actually plays a very important role in science. Okay. So remember that the second definition that I gave for statistics is that statistics is the discipline of learning about the world from data. Okay. Now, if you understand, if you ask what's the goal of science, the goal of science itself is actually to learn about the world, right? So physics, for example, tries to learn about the world, biology, chemistry. I mean, they maybe focus on different aspects of the world, but broadly, the goal of science itself is to learn about is to learn about the world. And of course, data is heavily used in almost every scientific field. Okay, so you see that how the definition of statistics and the definition of science itself kind of overlap, and so it's therefore unsurprising that statistics plays a key role in almost every scientific discipline. Okay, so you can actually see it in for example college majors. So if you
want to paint okay. It's all that is required. Go ahead.
Okay. So, for example, if you see most scientific majors, like even physics, biology, and things like that, they often have their own version of statistics courses. So either they ask the students to go take a course with the stat department, if there is a stat department in the university, or they have their own version of statistics classes, and often they use different names for essentially statistics. So for example, in biology, you hear the word biostatistics. Statistics applied to economic data is often goes under the name econometrics. You hear analytics. Physicists sometimes call it error analysis for essentially doing statistics. Chemistry have chemometrics and so on. Okay, so the ideas inside statistics play a key role in many scientific disciplines, and also it works the other way in the sense that many important ideas in statistics historically have been borrowed from people analyzing scientific data. So specifically scientists analyzing scientific data. Okay, so yeah, so the summary for this is that statistics is really very important in science. So I mean, it doesn't really matter what kind of science you do, you will be using ideas from statistics.
Online in town.
Okay, so
Dr.
the third,
Sorry, I hate
yes,
to cut you off, but if you don't mind, since I'm not host or co-host, could you mute everyone? Because I give you host access, otherwise I wouldn't
sure,
mute
sure,
people.
sure,
Thank you.
sure. Yeah, thank you. Okay, can I make you like co-host so you can do it, or?
I tried to make you co-host, but I wasn't able to, so I don't think you will be.
Okay.
You can try.
Okay, yeah, I'll just mute. So can I mute everybody at the same time?
Yeah, you can say mute all.
I guess where do I do that?
If you go to participants, it should say mute.
Okay.
Or if you click on the three buttons and then you can say mute all.
Oh yes, yeah, that's great. Yeah, I think I've done that. Thank you.
Oh, thank you.
Okay, so the third reason is that so this is I guess these days this is kind of obvious, but data and statistics are key to businesses and the government. Okay, so just to give you some specific examples, and then there are lots more examples that one can give here. If you see very successful companies like Amazon and Netflix, they do personalized say recommendations for their customers, and really statistical methods are key behind all those recommendation engines. You can, for example, banks and other lending agencies have for a very long time been using statistical models to assess, for example, creditworthiness of borrowers. Uh, Sports teams, for example, use stat methods for just improving performance of their own teams and also analyzing the opponents. Governments use statistics, for example, economic data such as GDP, unemployment, inflation, etc., to assess the health of the economy. Okay, and in the public health domain for clinical trials, statistical methods have been used for a very long time. Yeah, so basically, using ideas from statistics, can allow you to create new businesses to really address human needs. Okay. Okay, so those were my three reasons for why one should study statistics. Just to recap, one is some amount of literacy is really needed for everybody. Scientifically, statistics plays a very important role, and of course, for businesses and the government, you can use statistics to create, to create new enterprises and to address human needs. Okay, so next, I just wanted to say something about some what I think is the most important aspect of statistics, and this is probability. Okay, so statistics as a discipline is actually founded on what is called probability or probability theory. So probability theory is actually an older field compared to statistics. So it originated in maybe 1600s and 1700s when people were interested in games of chance, specifically gambling. So they wanted to, understand, how risk propagates in gambling and things like that. And that's where they started asking questions about this to mathematicians. And that was the origin of the field of probability. And then, in the 1800s, especially, and late 1700s, it was realized that this field, which originated from essentially gambling, can be turned into a very general framework for reasoning under uncertainty. Okay, so gambling, of course, there is uncertainty, but uncertainty, exists in pretty much every, field of life, really. And so probability theory can be used in places like that. So that realization really opened up all of these fields essentially. So this how probability theory works is actually easy to explain. So what probability theory does, it reduces reasoning under uncertainty to calculating probabilities based on modeling assumptions. Okay, so let me just give you some specific examples where probability theory can be applied, and it is applied in the field of statistics and in the other related fields that I will talk about a bit later. So, for example, suppose you want to answer this question. There's a particular email that comes into your, say, mailbox, and you want to figure out whether the email is spam. So, of course, you can look at it and determine that. But suppose you want to create a spam filter, which automatically looks at the email and determines if it's spam or not. Okay, so then the question that the software has to deal with is based on uncertainty, because it's uncertain whether the email is a real email or a spam email. So it has to do reasoning under uncertainty. Another example is, for example, if I ask, will it rain in Berkeley tomorrow? So that's also a question on uncertainty. So it comes under the ambit of probability theory. More such questions, if you're some government agency or even just a regular citizen and are wondering if the unemployment rate will go down next quarter compared to, let's say, this quarter. So that's again a question of uncertain reasoning. Just maybe at some other questions like that. A person in the workforce might wonder, if I take a break from work and go to school and get say a master's degree, would I get a much higher paying job than the job that I have now? Okay, so that's again a question in uncertainty. If I wake up with flu symptoms, let's say tomorrow, how do I tell if I actually have COVID or some other kind of flu? Okay, say a university, let's say Berkeley, decides to increase its police force by 20%, its campus police force, then it might be wondering what would be the reduction in on-campus incidents of crime. Okay, so all of these questions are essentially questions based in uncertainty. So uncertainty just means that the information that you have right now to answer a question like this is not enough to completely answer it. So you cannot logically deduce whether the answer to any of these questions is yes or no based on the available information. So that is called an uncertain situation. And any situation like that, you can apply probability theory. Okay, so how does probability really work? It just reduces the task of answering a question like this to a probability calculation, right? So for example, to answer whether the email is spam or not, you just turn that into a probability calculation. So you ask, what is then the probability that this particular email is spam, given the features of the email? So you have to somehow collect some features of the email, let's say like the number of words in the email, the number of dollar signs in the email, and things like that, because spam emails tend to have dollar signs. And you can feed it. You may have information on historical emails, a huge database of emails. So based on all the information that you have, you want to calculate now the probability that this specific email is spam. Okay. For the second question, will it rain tomorrow in Berkeley? You can again pose it as a problem in probability calculation. You're now calculating the probability that there'll be rain tomorrow in Berkeley, given say recent weather data. The third example, you want to calculate the probability that unemployment will go down next quarter, given recent economic data. And similarly, for the fourth example, so this is the master's example, you want to calculate the probability that you will get a high salary after your master's degree, given all the other relevant information that you may have about yourself and for other people in the workforce that are similar to you. Maybe you want to calculate the probability of COVID, given that you have flu this morning and some other relevant data. And the final example, also, you calculate the probability that the crime will go down, given the police force goes up by 20% and some other data. Okay, so the uncertainty question is now transferred into a probability calculation. Okay, so now the next step is how do you do these calculations? Of course, you can't do any calculation without some set of a framework and some set of assumptions. So those assumptions are called modeling. Okay, so in order to actually calculate any of these probabilities, you need what are called modeling assumptions. So these models are called statistical models or probability models. So these models are then invoked, which are essentially some basic assumptions which will allow you to calculate some probabilities. Then you use those models to calculate these probabilities. So that's basically how probability theory works. So let me give you a slightly more concrete example. So I'll try to work out the fifth example here. So suppose I wake up in the morning and I have flu. How do I calculate the probability that it's actually COVID? Okay, so so now, so one way of doing it, so there are many ways. One way is to use what is called Bayes rule. So this is a standard fact from probability. So this is the only equation I have in this talk. So hopefully this is not yeah, just if this is if you're not seeing equations like this, you can just wait for a little bit, and then the rest of the talk will be non-technical. So what Bayes rule says is, so suppose C is COVID, F is flu, and this other relevant data called B, that's background. So it writes the probability of COVID given flu, which is what I really want to calculate, because I have flu now. What's the probability that I have COVID? You flip that, so you write this probability in terms of the other conditional probabilities, where you write probability of flu given COVID and probability of flu given no COVID and the probability of COVID to begin with. Okay, so this is some complicated formula which you will learn if you take some probability class, and this tells you how to calculate this conditional probability of COVID given flu based on, say, other conditional probabilities such as flu given COVID and COVID to begin with. Okay, so now if you want to proceed with the calculation, you can try to supply values of these other probabilities. Okay, so for example, here is our one plausible set of probabilities, and the reasoning for this could be something like that. So suppose I say, okay, what's the probability that I'll get flu if I indeed have COVID? So that's the first probability. Now, if I indeed have COVID, then maybe flu symptoms are very likely. So I assign some high value to it, let's say 0.9 for the sake of argument. Then what is the probability of having flu if I do not have COVID? So of course, without COVID also, I may be having flu symptoms. Maybe my son had flu like a few days ago, and I've not been sleeping that well because of work recently. So there is some chance that I get flu without COVID. Let's say that's 0.6 for the sake of argument. And then the third probability is what's the probability of COVID given all the background information. So if I ignore my flu symptoms, what would be the probability of me getting COVID now? So then I say, okay, maybe I have not received any emails for work saying that somebody has COVID in my, my work area, let's say, and there's really not much COVID going on these days in the city, for example. So then I might assign a low value to it, which is 0.2. Okay, so you just assign some plausible probabilities based on some intuitive reasoning, and once you assign these, you can use that formula to calculate the probability that you actually want to calculate, which is the probability that you have COVID given your flu symptoms. Okay, so you just plug in all these numbers and calculate that probability. You get like maybe 25%. So in this case, it means that okay, it's much more likely that your flu symptoms um, given your flu symptoms, you actually do not have COVID. Okay, so this is a very crude and simple toy example of of how probability theory can be used to solve actually a real world problem. So in this example, this specification that we started out with, which is probability of getting flu given COVID and given no COVID, and the probability of COVID to begin with, this is what is called the probability or a statistical model. Okay, so this is the model, and what the purpose of the model always is to connect the observed data. So in this case, the observed data is that I have flu to the unknown parameter. In this case, the unknown parameter is whether I have COVID or not. Okay, so the connection between what you see, which is the data, and what you want to know about, which is some aspect of the world, that connection is given by a probability model or a statistical model. Okay, so the model is the thing that enables to do any computation. Now, of course, you may not like these numbers here. You may maybe you have a different background information. The information could be that somebody had COVID in your work area, say last week. Then you would have to change this model and go to a different model. But you need some model to actually do the calculation. Okay, so at a very high level, this is how probability works in any application. So to give you more examples, so let's go back to the email spam example, where the goal was to calculate the probability that a particular email is spam given features of the email and data on other emails. So here the model would depend on what this data on other emails is. So for example, you say the data on other emails could be you have a database of a whole bunch of emails. For each email, you have some set of features for the email, let's say the number of words in the email and the number of dollar signs and things like that. Yi is whether the email is spam or not. So you have to connect all of those to the particular email that you have, and also connect X to Y. Okay, so essentially the relation between X and Y needs to be learned based on the available data. And again, you can use models to do this. So these models will be more sophisticated than the simple model that I just talked about. So some models for this analysis could be, so these are some names that you may have heard of, things like logistic regression, tree-based models, and also neural nets and deep learning-based models. Okay. Okay, so in the rain example, so the rain example was how do you calculate the probability that it'll rain tomorrow in Berkeley given recent weather data in Berkeley and in say neighboring areas. So this is the recent weather. So you have to first quantify what you mean by data, and if you're doing this analysis, actually you should also have access to the data. So let's say you may have weather data from nearby locations for the past few days. So this would be an example of what is called a spatio-temporal prediction problem. So temporal because there's a time aspect to it, because you want to go from past information to the future information. Spatial because there is you have data at Berkeley and you also have data in nearby locations. Okay, so again there are in the field of statistics and related fields there are many models that you can use for this type of analysis. So I'm just throwing out some names here, things like Arimax, again, deep learning neural net models, and those based on Gaussian processes. Okay. Then you go to the unemployment example. The probability that you need to calculate is what's the probability that the unemployment goes down given recent economic data. Here one may have economic data for the past few quarters, let's say, things like GDP growth rate, inflation, and so on. And also maybe you can have other data on, say, Google Trends or job searches. So if more people are applying for jobs or searching for jobs, that means that the unemployment rate might be going high. So this is an example of what is called time series modeling. Because you have some macroeconomic indicators, you observe them in the past, and you want do some prediction into the future. So again, there are models which do this. So you should note that all of these are dealing with uncertain situations. So you cannot really logically deduce what would be the unemployment in the next quarter based on current information. So you have to use modeling and probability to solve these problems. Okay, just the final two examples. The salary example, you want to calculate probability that you will get a job with a much higher salary than your current salary, given that if you go to school and get a master's degree. Here you can have data, let's say from the current population survey, which is census data on people in the labor force. You can have data on their wages, education, experience, etc. And you want to use data. This database to answer the question. So this is an example of what is called regression modeling. So you can try to fit a model for wage based on education and experience and other covariates. You go to that model, you increase your education and see what wage the model gives you. So again, you can do this using regression modeling, but you can use neural nets for pretty much many things these days. So they're also fancier models. The crime and police example, so the university wants to know if it increases its police force by 20%, how much would the crime go down? So let's say you want to calculate the probability that the crime will go down by, say, at least 10%. So here you can have data on other university campuses, historical data from, say, UC Berkeley, maybe data from the city of Berkeley, things like that. So again, you can do some kind of a regression analysis, but there's also something called causal inference, because you want to attribute, the percentage of crime that will go down to this specific act of improving the police. Okay, so that's something called causal inference. Again, there are sophisticated models for doing that, based on like these DAGs and so on. Okay, so here, so what I want to say is that most statistics courses and most statisticians, they focus on specific kinds of models. So modeling is really most of the activity in this field. So if you go to, say, stats major in some university, the courses that they'll offer will all, many of the courses will be focused on models. Okay, so there'll be regression models, which really try to find the relationship between y and x. So for some y variable and some bunch of x variables, you want to find the relation. There is time series models for data which go in time and space, spatiotemporal models. Then there's something called non-parametric models. There's causal inference. You want to know what causes what. Something called mixture models for reducing the dimension of data and things like that. Okay, so just a few other things about models. Maybe you may have heard of these things if you have some scientific background. So all statistical models will involve something called parameters, which need to be learned from the data. Traditionally, you have models with a few number of parameters, but if you look at modern probabilistic or statistical models, especially those involving neural networks, they really have lots and lots of parameters. So now models with lots of parameters tend to be complicated. So there are some issues that they might run into in practice. So if you take stats courses, you will learn all these details about how modeling works and how to when they work, when they don't work, and things like that. Okay, so you can also ask, where do these models come from? So most users actually don't worry about where the models come from. They just use existing models implemented in software libraries. But the research, whoever research statisticians develop new models, and here again, ideas from all the fields are come together. In the modern day, a lot of the new model development is being done based on neural networks because of their successes in some other domains, which I'll mention a bit later. Okay, so maybe a few other things. There is something called Bayesian statistics, which I personally work on. So this is an important subfield of statistics where probability models are also used for parameters present inside larger models. Okay, so this is a very important set of ideas. It again originated in the sciences, and many of the ideas in Bayesian statistics actually came from physics. So it's not very commonly used with neural network models, but this is an area of active research. Okay, so in statistics, really there are two kinds of methods. One is Bayesian methods, and the other are frequentist methods. And in the historically, there have been fierce debates between people who believe in these different methods. Because sometimes they actually give you different answers. So philosophically, there are some differences. So the reason why you get into all of these is because fundamentally you're dealing with uncertainty. Because when you're dealing with uncertainty, it's hard to say what is right and what is wrong, because you don't know. That's you can think of an analogies to religion. Like you have debates about religion, you have also debates in fields like this. So this is, historically, this debate was much more fierce than it is currently, but many of the important topics of discussion are relevant, again, in this modern age of data science and AI and things like that. So I just want to mention it. So you might come across these terms when you actually look into the field of statistics. Okay, just other maybe topics. It's not all about modeling. Just to how to describe data, summarize data, visualize data. That is also, there is some science behind it, specialized software to do it. So you will, you see statisticians doing it. There's something called statistical inference, where how you go from specific data to say population level data. Design of experiments, like how do you run an experiment to collect the right kind of data to which will help you solve a problem of interest. Analysis of census data is historically very important. Like one of the reasons why the Indian Statistical Institute was actually set up is to do census and analyze census data. There's also a more mathematical field of statistics called theoretical statistics. I used to work on it. Um, um, yeah, so there you can view that as a subfield of mathematics, really, and also statistical case studies where you apply these ideas to specific scientific problems. Okay, so that was what I wanted to say about statistics. In the last few minutes, I just want to say something about how it relates to data science and machine learning. So statistics and data science, so if you ask most statisticians, including myself, we just feel that data science is just a new name for statistics. You go to anywhere, say Wikipedia or ask ChatGPT. You ask what is data science and what is statistics. You compare the answers. They really are roughly, they're the same thing. So of course, data science is the more modern name. Statistics is somewhat traditional. But both fields are so close. So if you go to say UC Berkeley, look at the statistics major, look at the data science major, see the courses listed in there, they overlap to a large degree. That being said, there are some minor differences in culture. So one is so to actually do data analysis, you need specialized software, because the software will it'll take care of implementing the statistical models typically. So statisticians used what is called R. R is a programming language for data analysis, while data science almost exclusively uses Python and specialized Python libraries such as I don't know, stats models or scikit-learn and things like that. Um, However, things are changing. So, you see many statistics courses with Python also these days. Yeah, but this is historically one difference. And the other thing is some data engineering skills, so such as working with large databases of data, such as SQL. They are emphasized a bit more in data science as opposed to statistics. Okay, so those are two minor differences that I can think of, but by and large, they are really, they have the same goals and they have the same foundations and they teach also very similar things. Okay, next, something about statistics and artificial intelligence and ML. So here, so as I mentioned before, so many scientific disciplines have their own version of statistics. For example, econometrics is really statistics applied to economic data and offered and taught in economics departments around the world. Biostatistics is statistics applied to biological genetic data. There's analytics, which is used in fields like operations research and marketing, etc. So similarly, the field of computer science also wanted to deal with uncertainty and applications, revolving around um, um, around the kind of topics that traditionally were thought about in computer science. And their version of statistics was called machine learning or artificial intelligence. Okay, so again, I mean, if you look at AI and ML and statistics, both again have roughly the same foundations in probability theory. So if you want to learn machine learning, you have to learn probability. If you want to learn statistics, you have to learn probability. So again, the foundational bedrock is basically the same. So that being said, AI and ML deserve significant credit for figuring out how to make neural networks work. So neural networks were around, since the 80s. There were some people in AI working on them back then, but they really couldn't make them work really, especially certainly not at the massive scale that you see them working now. And the field of statistics also, they played around a little bit with neural nets, but then they just gave up and tried to do other things. But some groups stuck by them and they figured out how to make them work. And these days, of course, the computer scientists built super useful automatic differentiation libraries, such as PyTorch and TensorFlow and things like that, which really, exploded the kind of things that you can do with these models. So that credit certainly the AI and the ML community, should be given. And also they have way cooler applications compared to statistics. So like self-driving cars, text generation, audio generation, video generation, robotics, and things like that. Okay, so they were thinking about these kind of problems for a long time, and now they've, essentially they figured out that you can make significant progress on these important problems using ideas from probabilistic modeling and specifically neural networks. Okay, so the successes have also rejuvenated statistics and other older fields such as applied mathematics, for example. So yeah, so I think we should all be thankful to them. Yeah, so on that note, I would like to stop. If you have questions, please feel free to ask.
Aditya, if you don't mind, can you give us an example with regarding to how the self-driving cars work?
Yes. So yeah. Yes. So self-driving cars. So I guess there are many aspects. So what the main aspect is certainly computer vision. Um, so the car has to be able to identify objects on the street, right? So it has to tell when the traffic signal is turning on, when there's a person actually crossing and you're at a pedestrian crossing zone and things like that. So it has to do object identification. Um, yeah, so that's really part of computer vision. So first of all, there is a huge engineering aspect, which maybe even you know more about. So how does it actually collect the data that enables it to solve these problems? And once it has the right kind of data, then the modeling aspect comes in. So at that point, things like neural networks can be used. Yeah, I mean, I don't personally work in self-driving cars, but at a high level, it's based on models which will, do specific tasks in computer vision.
Thank you.
There was a question by Ishri. She's asking, can I interpret as students wanting to do data science and AI should be also interested in statistics?
Yeah, so yeah, I mean, data science is not very different from statistics. Yeah, I mean, certainly any major in data science will go over the key concepts and topics in statistics also. Okay, so you don't really need to distinguish between them. If you have to make a choice, like if you have a data science major and a statistics major in a university, and you want to pick between them and you have no idea about the quality of instructors teaching both classes, then you can pick data science now because that's the cooler name. But other than that, you have to see who's teaching what courses, quality of instruction and things like that. AI, on the other hand, has a different focus. Yeah, traditional statistics knowledge is certainly helpful, but the kind of things that you will learn to do in an AI major or a machine learning major will be different from the kind of things that you will learn to do in a statistics major. So there is a bit more distinction, but certainly basic knowledge of statistics, modeling would be, is really invaluable to any of these fields.
Thank you for that. Another question we had was, what kind of courses would you recommend high schoolers to take in this field?
Yeah, so I think probability is super important. So if you can take a probability class, that will be helpful. Other, yeah, I mean, just so again, so you see that all of the scientific fields have courses in statistics, and the ideas are important in many of these fields. So some learning some common knowledge that, say, physics majors or chemistry majors would also know would be useful. So doing things like calculus and differential equations, learning more mathematics that really is the language of science, is certainly useful. You don't really have to take statistics early in high school. You can take it in college, but some of the basics such as probability are at least in my opinion more important.
And then one of the other questions here was, how does a person with a statistics background, like what are the job opportunities that they have?
Yeah, so I mean, many industries. So I mean, you can certainly apply to the tech world with statistics. There are a lot of statisticians working in, for example, Facebook and places like that. You can work in the government, Census Bureau, for example, or some government agencies which administer clinical trials. There is pharmaceutical companies. Yeah, I mean, there's a whole range of you know industry that people with stat degrees can apply to. Finance, for example, banks, hedge funds and things like that. Yeah, so I mean, depends on what one's interests are.
Got it. And then we had another question here from Ramana. How is Gen AI different from traditional AI ML, and any specific advanced models that are being used here?
So generative AI is also, I mean, so generative AI you can also think of as a traditional field where the goal is to generate things as opposed to understanding a relationship between one variable and another set of variables, etc. Again, traditionally they were the kind of models that are used to actually do these are changing. So previously they used, say, things like mixture models. Now almost exclusively it's based on deep learning based neural networks. Okay, now there are different kinds of neural nets, maybe diffusion models or whatever, normalizing flows and transformers and things like that. But the technology inside the modeling is changing. So so the current models can do things which are much more advanced compared to what the older models used to do. But in order to understand what the latest models are, I think some understanding of traditional methods would be useful, I think.
Saiphi's asking, how can statistics relate to the field of cybersecurity?
Cyber security, yeah, I'm not sure actually. Maybe you can use some modeling in fields like that, but I'm not familiar with cybersecurity. Sorry, I cannot answer that.
Mahika was asking if she's a student who wants to go into UCB and wants to study something in math business. What can I do to increase my chances? Because she wants to do something in stats, finance, or accounting. What will make her a diverse candidate?
Yeah, just I mean, take more math courses. I think that's helpful to all of these fields.
And then Sandy had a question about the applications of stats and data science in finance, if that's something that you would have.
Yeah, of course. I mean, finance. All the hedge funds are trying to create to even cash in on minor or very small signals. So they are using very high tech statistical modeling. Um, just and more generally, macroeconomic data is heavily subjected to statistical analysis. Again, I mean, this is a very, very it's a field where statistics has been used for a very long time.
And then another question was, is there internships that you might suggest for people that are interested in this field? Specific ones that they should be looking out for?
Like internships in the industry. Yeah, I mean, it depends on which level you're in. So if you're a college student who has done courses on these topics, then yes, I mean there would be many internship opportunities. If you're a high schooler, then it might be better to maybe learn a few things first before actually, working on actual applications.
For UCS, is the notion of doing data science as an undergrad considered incomplete, or does one have to do a PhD to do real data scientist work and be meaningful in their job?
That's a good question. Yeah, I mean, certainly many of the yeah, so they exist PhDs working on industry who are leading teams and so on. Um, as an undergrad, you can, yeah, I mean, there are many data science majors coming up right now. So you can certainly start your education there. But of course, to master any of these skills, you need to take more classes and you need more experience. So that's where certainly a master's degree and, even a PhD would be helpful. Because, the field is now somewhat rich, so you cannot hope to gain expertise with just a college degree.
And then thank you for that. And then Krishna was like, as a beginner in stats, I'd like to understand how organizations collect census data. Having the experience of working with confidence intervals to get estimates, but how is it possible?
Yeah, so again, I mean, all of these things are changing very rapidly. The way census data was collected, say 2 decades ago, is now very different from the way it's collected right now. So the field of statistics which deals with this is called sample surveys. So I mean, I'm again not super familiar with the latest technology, but the idea is you try to group the population into various subgroups, and you need to make sure that you collect enough data from each group to be able to say something about them. So you have to do something called stratified random sampling and things like that. And then, there is some, depending on the data limitations that you have to do some sophisticated models later on. But yeah, I mean, this is again, it's a very active field of study.
Yeah, just curious. I'm gonna follow up on that, but
Yeah.
Then,
when you said they take these samples, it seems very time consuming and super laborious. Is that just how they do it? They just power through and use manpower to get that done, or is there any smart ways that I'm just curious about this?
Yeah, I don't know what they're doing right now, actually. Maybe they do it online. Yeah, so maybe it's not. So traditionally, of course, they used to go door to door to collect data.
Actually, I can jump in. I worked in a census 2 years ago. They
Okay.
still do door to door and
Uh-huh.
collect the data, and then there is a random sampling on top of it.
I see. Okay, thank you. That's very helpful.
Mhm.
Yeah, so but certainly I think it'll be very different from the way they will do it maybe 10 years after. So yeah, I think these are important questions. More generally, polling is also somewhat sophisticated. You need yeah. So yeah,
All right, great. Thanks so much.
thank you.
Anand is asking, could you please elaborate on what applied mathematics is and what career options there are for those in that area?
Yeah, it's a great question. So applied mathematics also deals with models. But those models are slightly different flavor from the current kind of models that are used in stats. So they usually use ODE and PDE models. So ODE stands for an ordinary differential equation, PDE stands for a partial differential equation. So for example, in doing weather models, they use some complicated physics-based models. So now the thing is, uh, that field is also heavily transformed due to neural networks and deep learning right now. So many of the applied mathematicians are also using deep learning based methods. their fields of study. I personally think that applied mathematics is a very rich field. They they really are the field if to go to if you want to learn about differential equations, for example, and how differential equations are used to solve real problems. So that field will definitely exist. But some just taking a few applied math courses, mixing them with machine learning and other things is probably the way to go right now. I mean, again, probability is heavily used there also.
I get another question about scholarship opportunities, and also so this person said, what are some summer scholarship opportunities that could be useful when as a student and a senior in a college, or as any tips for students who want to switch from computer science to data science within their program? Will it make a big difference when it comes to job applications?
CS to data, yeah, I mean, I don't know about summer opportunities for high schoolers. Certainly, Berkeley will have some available opportunities. I have to check, which ones are currently being offered. About switching from CS to data science, yeah, I mean, it depends on what the kinds of jobs that you'll be applying to. I think having both in your resume is probably much more appealing than only having CS.
Okay, and then another question we had was, do you recommend SAS for stats or any other software applications?
So SAS is, first of all, private. I think it's not open source. So some companies and industries use that exclusively, I think. But these days, I don't think anybody would recommend that to do stats. These days, it's R, or even better is Python. So if you're starting, I don't see any reason why you should learn to use SAS unless you just end up in an industry or company that uses it. So.
And this is asking, would you recommend data science or statistics? And when it comes to both courses, which one or two programs have an overlap?
Yeah, I mean, you have to see. Yeah, so they'll teach you similar things. So you have to see, the quality of instruction. If you cannot, find any differences, then you can go with data science because that seems to be the cooler thing right now.
And then I think we have like 3 more questions before we wrap up. But Divya said, what unique opportunities can students pursue to advance their skill set in data science and AI? And how will they be positioning themselves for future exploration and growth in these fields? So as somebody that's early on or or like during the academic career of theirs, what could they be doing for them to be successful?
Yeah, I mean, so there are some foundational aspects in these fields, and then there are applications. So you should first learn the foundations, and then try to immerse yourself in a few applications. So the applications would really depend on what you're interested in. So yeah, that's the way it goes. Did I answer that question?
So I think more people are asking for their kids or for kids that are probably in high school or college, like what are the things that they should be doing outside or in school to make themselves like more well-rounded?
Yeah.
I mean, it's like probably like a kind of a variable question, but like what are things that I guess that they should be partaking in to advance their skill set?
Yeah, I mean, you can get a lot of information on these on YouTube and things like that. You can see the local universities and if they have some programs for high schoolers. I'm not super on top of these things right now, so but I can look up and send you some stuff later on.
And then in terms of industries too, somebody was asking, like, I guess I know it's very diverse, but is there certain industries that it's easy to get your foot in the door or also apply for internships or job opportunities compared to other industries? Like, is there some industries that are less regimented to get into?
Yeah, I mean, I'm not again super familiar with the industry, but yeah, I mean, so the range of industry jobs that you can apply for and go to with these skills is really vast. So you have to see what you're actually interested in, and then try to find people to talk to. That's how you'll get there.
Got it. And then Ramna had a question about training models. Is this different from any other type of statistics?
Training models, yeah, is so you can call that parameter estimation, because models are parameters and you want to estimate them. So there is a science behind it, which you will learn in stats. You'll also learn that in machine learning and so on. But training these large scale models that people use right now, they use a specific set of techniques. The older models which have fewer parameters, then there's a different set of techniques. So there are some differences, but yes, I mean, all of these is part of any of these fields.
Thank you. And then another question we had was, how would you see the combination of environmental science and data science majors for career perspective? Would that be a combination that would be well received?
Yeah, I mean, certainly environmental. Yeah, I would think so. Um, yeah, I mean, but I don't know what specific industry jobs would look at environmental science majors, but yeah, I mean, you can use data science methods, as I said, to pretty much any field. So certainly also the environment. Yeah.
And another question we had from GK was, is there any forms that are specific to AI and ML that you are aware of?
Any forums?
Forums, groups, discussions that will elaborate or further get into detail about the happening trends?
Yeah, I mean, of course, there'll be lots and lots of forums. You can maybe go to Twitter, follow some of these researchers doing it, and you can maybe that way go into certain groups. But yeah, I mean, the information on this is just really widely available. So yeah, I don't know of specific forums, but I would imagine that there'll be just tons of them. Yeah.
And then the last question we have from Damodar was, in terms of statistics, could we say that the major core subject is for data science, analytics, and AI, or does it also apply to any other fields of work?
Oh, statistics just yeah, all of these fields are doing similar things, and they can be applied to many kinds of applications, is what I would say.
Sorry, go ahead.
Yeah, so it's not like statistics is applied to ML. Yeah, you can say statistics apply to ML, but the core ideas exist both in statistics and also in ML. So what you specifically call it is less important, but the ideas are essentially the same. And then you can use these ideas to do actual applications, like you can do self-driving cars or to do financial modeling, or, a whole range of things.
Would you be able to talk a little bit more about new computing department at UC Berkeley?
Yeah, so this is a college. It's not a department. So yeah, it's a college. It's called CDSS. It's College of Data Science and Society. So this college has a bunch of departments inside it. One of them is statistics, computer science and engineering, and electrical engineering is also in there, but they're also in the School of Computing. We also have computational biology, and there will be new departments coming up, more interdisciplinary departments. So this college will be administering the data science major and also the statistics major. So yeah, I mean, it's an exciting, development on campus. In fact, I think it's the first college to come up in a very long time, first new college to come up. So they're building a big building for this, to accommodate all the departments in the college. So there will be lots of new hires. yeah, I think it's a super exciting thing. Yeah.
I think that was the end of our question. I know we went over a little bit over time, but we appreciate you coming and presenting with us today. And there is a recording of this session which will be sent out to you guys. And somebody was asking if they would be able to get the slides because some of their family members were not able to attend this. So if there's a way of you sending the slides out so that they can send this out with the team, the meeting link as well. And
yeah, I'll be happy to share the slides, of course. Yeah, just tell me where to send them.
Okay, thank you so much. With Uncle, is there anything else on your end?
No, I think we are good. And thank you, Aditya, and thank you, Ananya.
Thank you very much for having me. Thanks for all the questions. And have a great Sunday. Thank you.
Thank you
Have
so
a good
much.
one.